Welcome. Friends, I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know where in the world are you listening from? Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into Earth's deepest and most hidden timeline, the 4.5 billion years that shaped every grain of sand beneath your feet. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. 4.5 billion years ago, there is no Earth as we know it. There is only a disk of dust and gas, spinning slowly around a young star that burns with the fierce inconsistency of stellar youth. Within this disk, particles no larger than grains of sand begin their patient work of accumulation. They drift and collide in the vacuum, sticking together through forces so gentle that a human breath could scatter them across light years. Yet, here, in the silence between worlds, these microscopic encounters carry the weight of future continents. The process unfolds with geological patience. Individual dust grains, each containing elements forged in the nuclear furnaces of dying stars, find each other across vast distances. They cling together through electrostatic forces weaker than the attraction between socks emerging from a clothes dryer. Over thousands of years, these clusters grow from the size of pebbles to boulders, from boulders to mountains floating in space. Gravity, that most persistent of architects, begins to assert its influence over matter that has never known the luxury of solid ground. These early aggregations, called planetesimals, orbit the infant sun in elliptical paths that intersect with mathematical inevitability. When they collide, they do not shatter like earthly rocks meeting at highway speeds. Instead, they merge with the slow determination of ice flows joining in an Arctic spring. Each impact adds mass, and mass adds gravitational pull. And gravitational pull sweeps up more debris in an accelerating cycle of planetary construction that spans tens of millions of years. The proto-Earth that emerges from this cosmic assembly process bears no resemblance to the blue marble suspended in space photographs. Its surface radiates heat at temperatures that would vaporize lead, glowing with the deep cherry-red luminescence of metal fresh from a forge. The atmosphere, if such a term applies to this early stage, consists primarily of hydrogen and helium captured directly from the solar nebula gases, so light they will eventually escape Earth's gravitational embrace and drift back into interstellar space, leaving the planet temporarily naked beneath the cosmic dark. Scientists call this epoch the Hadean Eon, named for Hades, the ancient Greek underworld where nothing grows and shadows dance in eternal twilight. The name proves oddly appropriate. This earliest chapter of Earth's biography stretches from the planet's formation at 454 billion years ago to roughly 4 billion years ago, a span of time so vast that it contains within itself dozens of geological periods, each longer than the entire history of complex life. During these 540 million years, Earth learns the fundamental physics of planetary existence through trial and error conducted on a global scale. The surface temperature hovers around 200 degrees Celsius, hot enough to keep silicate rock in a permanently molten state, yet cool enough that gravity can begin the slow work of chemical differentiation. Iron and nickel, the heaviest elements in Earth's early composition, begin their descent toward the planetary core like metallic precipitation falling upward through an ocean of liquid stone. This separation of materials by density creates Earth's first major geological structure, a heart of dense metal surrounded by a mantle of lighter rock, all overlaid by the thinnest possible skin of cooling crust that reforms as quickly as it fractures. The differentiation process releases tremendous quantities of heat through gravitational potential energy conversion, the same physics that warms your hands when you rub them together, scaled up to planetary proportions. This internal heat source ensures that Earth remains molten for millions of years after the initial bombardment of planetesimal impacts begins to subside. The planet glows from within like a cosmic ember, radiating infrared light into the void while slowly, imperceptibly, beginning its long cooling toward a state that might someday support liquid water. No witness exists to record these transformations. No life has yet discovered the chemical pathways that lead from simple organic molecules to self-replication and metabolism. The concept of observation itself remains billions of years in the future. Earth spins alone in the darkness of space, its surface cooling and reheating in cycles that follow the chaotic rhythm of asteroid and comet impacts. Each collision adds not only mass and heat, but also angular momentum that gradually slows the planet's rotation from what theoretical models suggest might have been a 6-hour day to something approaching our familiar 24-hour cycle. The Moon has not yet formed, and its absence creates a fundamentally different Earth than the one we inhabit today. Without a large satellite's gravitational influence, the planet wobbles dramatically on its rotational axis, creating temperature and seasonal variations that would render climate prediction impossible. The lack of tidal forces also means no regular rhythm of rising and falling seas, no twice-daily mixing of coastal waters, no lunar calendar to mark the passage of time for future organisms that might evolve to depend on such celestial clockwork. Even the sun burns with the inconsistency of stellar youth during these early epochs. Young stars commonly experience brightness variations of 10 to 20% as their nuclear fusion processes find equilibrium between gravitational collapse and radiative pressure. These fluctuations would trigger ice ages or global warming events on the modern Earth. But the Hadean planet absorbs such variations without response. No ice exists to melt, no vegetation exists to wither or flourish. No atmospheric chemistry complex enough to amplify or dampen solar changes through feedback mechanisms. The sky above this molten world glows not blue, but the color of heated metal orange, fading to red at the horizons where atmospheric density creates a greenhouse effect unlike anything in Earth's later history. No clouds form in this early atmosphere, because water exists only as superheated vapor, if it exists at all. Most of Earth's future oceans remain locked in ice within comets and asteroids orbiting in the cold outer reaches of the solar system, waiting for orbital mechanics to deliver them to the inner planets over the coming hundreds of millions of years. Yet even in this apparent desolation, the seeds of future complexity take root. The same gravitational processes that separate iron from rock also concentrate rare elements into distinct geological zones. Radioactive isotopes, distributed randomly through the initial planetesimal collisions, begin to decay at rates that will provide steady internal heating for billions of years to come. The planet's magnetic field, generated by convection currents in the liquid metal core, starts to deflect harmful solar radiation and create the protective envelope that will eventually allow life to persist on the surface. In the cosmic silence of deep space, with no sound carrying through the vacuum between worlds, Earth begins its slow transformation from a ball of molten rock into something capable of supporting the intricate chemical processes that will, in unimaginable stretches of future time, give rise to photosynthesis and predation, to forests and fossil fuels, to consciousness itself contemplating its own origins in the light of ancient stars, But for now, there is only heat and time and the patient alchemy of planetary formation unfolding beneath a sky that has never known the touch of wind or rain. The magma ocean that covers the Hadean Earth moves with the slow persistence of geological time made liquid. Beneath its glowing surface, convection currents carry heat from the planet's molten interior in patterns that will persist for millions of years, creating the first rhythms in Earth's planetary circulation. These currents rise and fall like the breathing of some vast sleeping entity, transferring energy from core to surface in cycles measured not in minutes or hours, but in millennia. As the bombardment of planetesimals gradually subsides, leaving longer intervals between major impacts, the magma ocean begins its first tentative experiments with solidification. Thin crusts of basaltic rock form where the surface cools most rapidly, creating islands of solid stone that float like scum on the molten sea. These proto-continents last only briefly before the next asteroid impact or convective upwelling destroys them, melting the rock back into the global ocean of liquid stone. It is a cycle of creation and destruction that operates on timescales so vast that human language lacks adequate metaphors for such patience. The composition of this early crust differs significantly from the granite and sedimentary rocks that will eventually form Earth's continental masses. Rich in magnesium and iron, dark in color and dense in structure. It resembles more closely the ocean floor that lies hidden beneath modern seas than the familiar landscapes of mountains and plains. When these early crustal patches do manage to persist for thousands of years before their inevitable destruction, they create the first solid surfaces in Earth's history, places where, in some distant future, the first primitive organisms might find purchase against the endless fluidity of their molten world. The atmosphere above this magma ocean consists primarily of water vapor, carbon dioxide, and nitrogen, with trace amounts of sulfur compounds that give the air a chemical signature unlike anything that will exist in Earth's later epochs. The water vapor content reaches levels of saturation impossible under modern atmospheric conditions, creating a greenhouse effect so intense that surface temperatures remain hundreds of degrees above the boiling point of water at sea level pressure. This superheated steam atmosphere extends dozens of kilometers above the planetary surface, glowing with thermal radiation like the aurora of a world that has forgotten how to be cool. Yet even within this apparently hostile environment, the fundamental chemical processes that will eventually enable life begin their slow exploration of molecular possibility. Organic compounds form spontaneously in the upper atmosphere where solar ultraviolet radiation provides the energy needed to forge carbon-hydrogen bonds from simpler precursor molecules. These early organic materials rain down onto the magma ocean, where they are immediately destroyed by the intense heat, only to reform again in the cooler regions of the upper atmosphere in an endless cycle of chemical experimentation. The magnetic field generated by Earth's liquid iron core during this period operates at strengths several times greater than the modern planetary magnetic field, deflecting solar wind particles with such efficiency that the atmosphere remains largely intact despite the absence of a protective ozone layer. This magnetic shield proves crucial for Earth's long-term atmospheric evolution, preventing the gradual erosion of water vapor and carbon dioxide that has left Mars with its thin, cold atmosphere. Without this early magnetic protection, Earth might have followed a similar evolutionary pathway toward planetary desiccation. The rotation period of the Hadean Earth remains significantly shorter than our familiar 24-hour day, with theoretical models suggesting rotation periods between 6 and 10 hours, depending on the timing and magnitude of major impact events. This rapid rotation creates powerful Coriolis effects that drive atmospheric circulation patterns unlike anything in Earth's later climate history. Storm systems, if they can be called storms in an atmosphere composed primarily of superheated steam, develop with rotational velocities that would dwarf the most powerful hurricanes of modern times. The gravitational influence of the forming moon, still embedded within the debris disk created by the giant impact that will eventually separate it from Earth, creates tidal effects on the magma ocean that exceed anything experienced by modern oceans. These tidal forces stretch and compress the molten surface by hundreds of meters twice each day, generating additional heat through tidal friction and contributing to the planet's prolonged molten state. The energy dissipated by these tidal interactions gradually slows Earth's rotation while simultaneously pushing the moon into higher orbits, beginning the celestial dance that will eventually stabilize both bodies. Volcanic activity during the Hadean operates on scales that make modern volcanic eruptions appear modest by comparison. Entire regions of the protocrust periodically collapse back into the magma ocean, creating volcanic episodes that last for centuries and release quantities of gas and ash sufficient to alter atmospheric composition on a global scale. These events redistribute chemical elements across the planetary surface, concentrating rare metals and radioactive isotopes in patterns that will influence geological processes for billions of years to come. The boundary between day and night on this early Earth remains sharply defined despite the thick atmosphere, creating temperature differentials that drive convective circulation with tremendous energy. The day side of the planet radiates heat at wavelengths that peak in the near-infrared spectrum, while the night side cools sufficiently to allow the first tentative condensation of water vapor into droplets that immediately evaporate upon contact with the superheated surface. These brief moments of liquid water existence represent Earth's first experiments with the phase transitions that will eventually enable the formation of stable oceans. Chemical weathering processes begin their work even in this molten environment, as atmospheric gases react with exposed crustal materials to create the first mineral assemblages that differ from the original planetary building materials. Sulfur dioxide and hydrogen sulfide interact with metal-rich basalts to form sulfide minerals that will become important components of Earth's early sedimentary record. Carbon dioxide dissolves in the brief pools of liquid water that form in shadowed regions, creating carbonic acid solutions that begin the slow process of chemical erosion that will eventually help stabilize Earth's climate through the carbonate-silicate cycle. The absence of plate tectonics during this early period means that heat transfer from the interior occurs primarily through massive volcanic plumes that puncture the thin crust like hot springs breaking through ice on a frozen lake. These plumes create circular patterns of crustal deformation visible from space as concentric rings of uplifted and subsided terrain. The largest of these thermal anomalies persist for millions of years, creating the first semi-permanent geographical features in Earth's geological record. As the Hadean eon progresses toward its eventual conclusion, the frequency of major impact events decreases exponentially, following the mathematical pattern of debris clearing that characterizes the late stages of planetary formation in all solar systems. This gradual reduction in bombardment intensity allows crustal materials to persist for increasingly longer periods before destruction, setting the stage for the eventual formation of stable continental masses. The magma ocean begins its slow retreat toward the planetary interior, leaving behind the first permanent traces of solid ground in Earth's 4 billion-year journey toward the world we know today. In the darkness of space, approximately 50 million years after Earth's initial formation, a wandering planet the size of Mars follows an orbital trajectory that will intersect with our world's path around the Sun. This object, which planetary scientists have named Theia after the Greek Titaness who gave birth to the moon goddess Selene, approaches Earth with the inevitability of celestial mechanics operating across vast scales of time and distance. Neither world possesses consciousness to recognize the approaching collision that will fundamentally alter the architecture of the inner solar system. The impact occurs at a relative velocity of roughly 11 kilometers per second, a speed that transforms solid matter into plasma and vapor in the microseconds following contact. Theia strikes Earth at an oblique angle, delivering a glancing blow that avoids the complete destruction either planet would experience in a head-on collision. Instead, the impact excavates enormous quantities of material from both bodies, launching molten rock and metal into Earth orbit with sufficient velocity to escape the immediate gravitational pull of the combined planetary mass. The energy released in this collision exceeds the total nuclear arsenal of human civilization by factors measured in millions. The impact site, located somewhere in what will eventually become the Pacific Ocean basin, vaporizes instantly, creating a crater that extends through Earth's crust and deep into the underlying mantle. Shock waves propagate through the planet's interior at velocities approaching the speed of sound in rock, creating seismic disturbances that temporarily liquefy solid materials thousands of kilometers from the impact zone. Within hours of the collision, a ring of debris begins to coalesce in Earth orbit, composed of material from both the impactor and the target planet. This debris disk contains roughly 3 times the mass of the modern Moon, distributed in a flattened ring that extends from just above Earth's surface to distances of several planetary radii. The particles within this ring range in size from microscopic dust grains to chunks of molten rock larger than mountains, all orbiting Earth with periods measured in hours rather than the month-long orbital period of the fully formed Moon. The gravitational dynamics within this debris ring operate according to the same physical principles that govern all accretionary disks, from the formation of planets around young stars to the creation of Saturn's intricate ring system. Larger particles sweep up smaller ones through gravitational attraction, growing steadily in mass and gravitational influence. The process proceeds with remarkable efficiency, concentrating the majority of the ring material into a single dominant body within approximately 1,000 years, a formation timescale that represents mere moments in the context of planetary evolution. The newly formed Moon emerges from this accretionary process at an orbital distance of roughly 25,000 kilometers from Earth's surface, compared to the modern lunar distance of 384,000 kilometers. At this proximity, the Moon appears 70 times larger in Earth's sky than it does today, subtending an angular diameter of nearly 40 degrees and creating tidal effects that dwarf anything experienced in Earth's later history. The gravitational forces between the two bodies generate tidal bulges in Earth's molten surface that rise and fall by thousands of meters twice each day. These extreme tidal forces create a phenomenon that planetary scientists term tidal locking friction, which gradually transfers angular momentum from Earth's rotation to the Moon's orbital motion. The process slows Earth's rotation period from its initial 6-hour day toward longer periods, while simultaneously pushing the Moon into higher orbits through conservation of angular momentum. This gravitational interaction will continue for billions of years, eventually stabilizing both bodies in the configuration we observe today. The chemical composition of the Moon, as revealed by analysis of Apollo samples returned during the 1960s and 1970s, provides compelling evidence for this giant impact hypothesis. Lunar rocks show isotopic signatures nearly identical to Earth's mantle materials, suggesting that both bodies formed from the same reservoir of solar system matter. However, the Moon displays a significant depletion in volatile elements like water and atmospheric gases, consistent with formation in the high-temperature environment created by the impact event. The immediate aftermath of the Moon-forming impact leaves Earth's surface in a state even more molten and chaotic than during the initial planetary accretion phase. The additional heat input from the collision raises global surface temperatures by several hundred degrees, ensuring that any solid crust formed during the preceding millions of years returns to liquid form. The planet glows with thermal radiation across the entire electromagnetic spectrum, appearing as a second star when viewed from the orbital distance of Mars. Atmospheric conditions following the impact differ dramatically from the pre-collision environment. The tremendous energy release vaporizes significant quantities of crustal and mantle materials, injecting silicon, aluminum, and iron vapors into the atmosphere along with the existing complement of water vapor and carbon dioxide. This metal-enriched atmosphere creates optical properties unlike anything in Earth's later atmospheric evolution, scattering light in ways that produce spectacular auroral displays as the vapor condenses and precipitates back to the surface. The formation of the Moon also establishes Earth's axial tilt at approximately 23 degrees, creating the seasonal variations that will become crucial for climate stability and biological evolution in the distant future. Without the Moon's gravitational influence, Earth's rotational axis would wander chaotically due to gravitational perturbations from Jupiter and other large planets, creating climate variations that would inhibit the development of complex life forms. The Moon serves as a celestial anchor, maintaining Earth's axial orientation within narrow bounds for billions of years. The debris remaining in Earth orbit after the Moon's formation continues to rain down on both planetary surfaces for millions of years following the initial impact. This extended bombardment phase creates the heavily cratered terrain visible on the Moon's surface today, while simultaneously delivering additional heat and material to Earth's evolving crust. The largest of these secondary impacts excavate craters hundreds of kilometers in diameter, creating temporary seas of molten rock that slowly cool and solidify into the first stable crustal formations. As the Moon gradually recedes from Earth due to tidal friction, its apparent size in the sky decreases correspondingly, and the magnitude of tidal effects diminishes toward the levels that will eventually allow stable ocean formation. The gravitational dance between Earth and Moon enters a phase that will persist essentially unchanged for the remaining 4 billion years of Earth's evolution, providing the stable celestial mechanics necessary for the development of atmospheric chemistry, plate tectonics, and ultimately the emergence of life itself. The giant impact that creates the Moon represents perhaps the most violent event in Earth's history after the initial planetary formation phase, yet it also establishes the conditions that make Earth uniquely suitable for supporting complex life. Without the Moon's stabilizing influence on axial tilt, without the tidal mixing that will eventually help concentrate organic molecules in coastal environments, and without the gradual slowing of Earth's rotation to permit the development of stable weather patterns, our planet might have followed a very different evolutionary pathway through deep time. As the debris from the Moon-forming impact settles and the newly formed lunar companion begins its slow retreat from Earth's immediate vicinity, the planet's atmosphere enters a phase of gradual cooling that will span millions of years. The superheated steam that comprises the majority of atmospheric mass during the immediate post-impact period begins to reach the critical threshold where water vapor can transition from gas to liquid, a temperature boundary that will determine whether Earth develops permanent oceans or follows the evolutionary pathway of Venus toward a runaway greenhouse effect. The cooling process unfolds with geological patience, driven primarily by radiation of thermal energy into the vacuum of space. Earth's surface temperature drops from the molten rock temperatures of 100–200 degrees Celsius toward the more moderate range of several hundred degrees where liquid water becomes theoretically possible. This temperature decline proceeds unevenly across the planetary surface, with polar regions cooling more rapidly than equatorial zones due to the geometry of solar heating and the planet's axial tilt established by the lunar impact. When atmospheric temperatures first drop below the critical point of water at 374 degrees Celsius, the physics of phase transition begins to operate on a planetary scale. Water vapor that has circulated freely through the atmosphere for millions of years starts to condense into microscopic droplets, forming clouds unlike anything that will exist in Earth's later atmospheric evolution. These early clouds consist of superheated water droplets suspended in an atmosphere still dominated by carbon dioxide and other volcanic gases, creating optical properties that scatter sunlight in ways that paint the sky in hues of deep red and orange. The first raindrops to fall on Earth's surface represent a moment of profound planetary transformation. Though no witness exists to observe this transition from a steam world to a water world, these initial precipitation events occur sporadically, as localized cooling allows temporary condensation of atmospheric moisture that immediately evaporates upon contact with the still hot crustal surface. The raindrops themselves carry temperatures approaching the boiling point of water under modern atmospheric conditions, hissing into steam the moment they touch solid rock. As surface temperatures continue their gradual decline, the duration of these rainfall events increases from seconds to minutes, from minutes to hours. Eventually, atmospheric cooling reaches the threshold where water droplets can persist on the planetary surface for extended periods before evaporating, creating the first temporary pools of liquid water in Earth's history. These ephemeral seas form primarily in the polar regions and in the shadows of the largest topographical features, where solar heating remains insufficient to immediately vaporize the accumulated precipitation. The chemistry of this early rainfall differs dramatically from the pure water that will characterize later precipitation cycles. Atmospheric water vapor dissolves significant quantities of carbon dioxide, sulfur dioxide, and other volcanic gases as it condenses, creating acidic solutions with pH levels comparable to modern industrial acid rain. This chemical loading proves crucial for the eventual development of Earth's climate system, as carbonic acid precipitation begins the process of chemical weathering that will eventually regulate atmospheric carbon dioxide concentrations through the carbonate-silicate cycle. Theoretical models suggest that the transition from a steam atmosphere to stable liquid water oceans requires approximately 10 million years of continuous cooling, though the exact duration depends sensitively on atmospheric composition and the rate of heat loss to space. During this extended period, Earth experiences rainfall events that dwarf any precipitation in the planet's later climate history. The sheer volume of water vapor contained in the early atmosphere means that when condensation begins in earnest, it continues virtually without interruption for geological ages. The sound of this primordial rain falling on molten rock creates the first sustained acoustic environment in Earth's history. Though the dense atmospheric composition carries sound waves with frequencies and amplitudes unlike anything in modern terrestrial acoustics, the constant percussion of water droplets striking stone generates a planetary percussion that resonates through the atmosphere for millions of years, punctuated by the sharper sounds of steam explosions where concentrated rainfall encounters particularly hot crustal surfaces. Erosion begins its work during these early rainfall events, carving the first channels and valleys in Earth's primitive topography. The chemical aggressiveness of the acidic precipitation accelerates weathering processes beyond anything experienced on the modern Earth, dissolving minerals from exposed rock surfaces and transporting dissolved chemicals toward the lowest elevations where temporary lakes begin to accumulate. These early erosional processes create the first sedimentary deposits, as weathered rock particles settle out of the acidic water in patterns that will be preserved in Earth's earliest geological record. The formation of stable water bodies also establishes the first hydrological cycle. As evaporation from temporary seas returns moisture to the atmosphere where it can condense and precipitate again in an endless circulation of water between liquid and gaseous phases. This cycle operates with tremendous energy during the early stages, driven by the high surface temperatures that promote rapid evaporation and the dense atmospheric water content that enables intensive precipitation. The result is a global climate system dominated by water transport on scales that exceed modern hurricane systems by orders of magnitude. Tidal forces from the nearby Moon create additional complexity in these early hydrological systems, as the extreme gravitational effects generate tidal ranges in the temporary seas that expose and submerge vast areas of crustal surface twice each day. These tidal zones become natural laboratories for chemical weathering and mineral concentration, as the regular cycling between aqueous and atmospheric environments accelerates chemical reactions that might otherwise require millions of years to reach completion. The gradual accumulation of liquid water in topographical depressions marks the beginning of Earth's transition from a volcanic planet to a water world. As more precipitation persists on the surface for extended periods, isolated pools begin to merge into larger bodies of water that eventually connect to form the first primitive oceans. These early seas differ chemically and physically from modern oceans, containing dissolved minerals in concentrations that would be toxic to contemporary marine life and operating at temperatures that exceed the thermal tolerance of all known biological systems. The atmospheric pressure during this transitional period remains several times higher than modern sea level pressure due to the large quantities of carbon dioxide and water vapor still present in gaseous form. This dense atmosphere creates greenhouse conditions that maintain global temperatures well above the freezing point of water, even as the planet gradually cools toward the temperature range that will eventually support biological processes. The interplay between atmospheric composition, surface temperature, and hydrological cycling establishes feedback mechanisms that will regulate Earth's climate for billions of years to come. Cloud formation during this early atmospheric evolution creates the first global weather systems, as water vapor condenses preferentially in regions of atmospheric cooling and rising air masses. These early meteorological patterns establish circulation cells that transport heat and moisture between different latitudes, beginning the atmospheric mixing processes that will eventually distribute chemical elements and energy across the planetary surface with the efficiency necessary for biological evolution. As the age of perpetual rain gradually comes to an end, Earth emerges with a fundamentally altered surface covered by vast seas of hot, chemically aggressive water. The stage is set for the next phase of planetary evolution, where these primitive oceans will serve as the crucible for chemical processes that will eventually give rise to the first self-replicating molecules and the beginning of life's long journey toward complexity and consciousness. The first permanent oceans that cover the Archean Earth stretch from horizon to horizon without interruption, creating a water world more complete than any science fiction imagination. No continents rise above these ancient seas. No islands break the monotony of liquid surface extending in all directions under skies that have never known the green of photosynthesis or the blue of oxygen-rich atmosphere. These primordial waters exist in a state of chemical and thermal equilibrium, unlike anything that will characterize Earth's later marine environments, operating according to physical principles that govern fluid dynamics on a planetary scale. The temperature of these early oceans hovers near 80 degrees Celsius in the equatorial regions, cooling to perhaps 60 degrees at the poles, conditions that would prove instantly lethal to most contemporary marine organisms, yet represent a dramatic cooling from the superheated steam that dominated Earth's earlier atmospheric evolution. This thermal gradient drives circulation patterns of tremendous scope and intensity, creating global currents that transport heat and dissolve chemicals between different latitudes with efficiency that dwarfs modern oceanic circulation systems. The chemistry of these Archean seas differs so fundamentally from modern seawater that they might be considered an entirely different type of liquid altogether. Dissolved iron concentrations reach levels thousands of times higher than contemporary oceans, giving the water a distinctive greenish-brown coloration that absorbs and scatters sunlight in ways that create optical effects unknown in Earth's later marine environments. Hydrogen sulfide bubbles continuously from underwater volcanic vents, creating localized zones of chemical activity where mineral precipitation occurs in patterns that will be preserved in the geological record for billions of years. The absence of free oxygen in these early oceans means that chemical reactions proceed according to pathways that have become extinct in Earth's oxidized modern environment. Methane and hydrogen gas dissolve readily in the iron-rich waters, creating reducing conditions that favor the formation of organic compounds through purely inorganic chemical processes. These spontaneous synthesis reactions occur continuously throughout the water column, generating complex carbon-based molecules that rain down onto the ocean floor in organic sediments that will eventually become some of Earth's earliest fossil deposits. The pH of these primitive seas remains highly acidic, with values approaching those of modern industrial waste streams due to the continuous dissolution of atmospheric carbon dioxide and sulfur compounds in the absence of biological buffering mechanisms. This chemical aggressiveness accelerates weathering processes on the ocean floor and along the shorelines of the few volcanic islands that occasionally emerge from the depths, contributing dissolved minerals to seawater at rates that exceed modern inputs by orders of magnitude. Tidal forces from the much closer Moon create extraordinary effects in these global oceans, generating tidal ranges that exceed 100 meters in some coastal regions. These extreme tides expose vast areas of ocean floor twice each day, creating intertidal zones that span hundreds of kilometers and operate as natural chemical reactors where concentrated seawater undergoes repeated cycles of evaporation and dilution. The energy dissipated by these massive tidal movements contributes additional heat to the ocean system, maintaining temperatures well above the range that will eventually support primitive life forms. Pressure conditions at the bottom of these early oceans exceed modern deep-sea pressures due to the greater density of the iron-rich seawater and the higher atmospheric pressure that prevails during this epoch. These extreme pressure environments create unique mineral assemblages that form only under conditions no longer present on Earth's surface, producing rock types that serve as diagnostic indicators of Archean ocean chemistry when discovered in the modern geological record. The absence of biological productivity means that these early oceans operate as purely physical and chemical systems, governed entirely by thermodynamic principles without the complex feedback mechanisms that living organisms will eventually introduce. Nutrient cycling occurs through purely inorganic processes, as chemical elements move between dissolved and solid phases according to temperature and pressure gradients rather than biological uptake and release. This simplified chemistry creates conditions that favor the concentration of trace elements and rare earth metals in patterns that will become crucial for the eventual emergence of metabolic processes. Evaporation from the ocean surface during this period operates at rates that exceed modern evaporation by factors of 10 or more, driven by the high surface temperatures and the low atmospheric humidity that characterizes the early Earth's climate system. This intense evaporation creates vast salt deposits in isolated basins where seawater becomes concentrated beyond the saturation point of dissolved minerals. These evaporate formations represent some of Earth's earliest sedimentary deposits, preserving chemical signatures of early ocean composition in crystalline form. The sound environment within these Archean oceans differs dramatically from the acoustic properties of modern marine environments. The high dissolved mineral content and elevated temperatures create sound transmission characteristics that allow acoustic waves to travel much greater distances through the water column. Underwater volcanic activity generates continuous background noise as molten rock contacts seawater, creating steam explosions and thermal shock waves that propagate across entire ocean basins. Chemical stratification within the water column develops according to density gradients that reflect temperature and dissolved mineral concentrations rather than biological productivity patterns. Dense, iron-rich waters sink toward the ocean floor, while lighter, hydrogen-rich waters rise toward the surface, creating distinct chemical layers that persist for thousands of years without the mixing that biological activity will eventually introduce to marine systems. The interaction between these primitive oceans and the early atmosphere establishes the first global chemical cycles. As gases dissolve into seawater and precipitate back into the atmosphere according to temperature and pressure variations, carbon dioxide cycles between atmospheric and oceanic reservoirs through purely physical processes, establishing the foundation for the carbonate chemistry that will eventually regulate Earth's climate through biological mediation. Mineral precipitation from these supersaturated ancient seas creates the first extensive sedimentary deposits. As dissolved chemicals reach saturation concentrations and crystallize out of solution onto the ocean floor. These chemical sediments form in layered deposits that record fluctuations in ocean chemistry and temperature over geological time, providing paleoclimatologists with evidence of environmental conditions that prevailed billions of years before life began to influence Earth's surface chemistry. The vast expanse of these early oceans creates weather systems of unprecedented scale and intensity. As evaporation and condensation operate across ocean basins thousands of kilometers in extent, storm systems develop with rotational velocities and precipitation rates that dwarf modern hurricanes, driven by the tremendous temperature gradients between ocean surface and atmosphere that characterize this early phase of Earth's climate evolution. As these Archean oceans persist for hundreds of millions of years without biological influence, they gradually approach chemical equilibrium with the atmosphere and crustal rocks through weathering and gas exchange processes. This slow approach toward thermodynamic stability creates increasingly favorable conditions for the complex chemical reactions that will eventually give rise to self-replicating molecules and the first primitive life forms, setting the stage for biology to begin its transformation of Earth's surface environments. In the chemical depths of the Archean oceans, where sunlight penetrates only the uppermost layers of iron-rich water, molecular processes begin that operate according to principles entirely foreign to the oxygen-dependent biochemistry that will eventually dominate Earth's biosphere. These early chemical reactions proceed without the guidance of evolved enzymes or the organization of cellular structures, yet they accomplish transformations of matter and energy that represent the first tentative steps toward the metabolism that characterizes all living systems. The protagonists of these ancient chemical dramas are bacteria so primitive that they barely qualify as life by modern definitions, yet they possess the fundamental capability that distinguishes living matter from mere chemical complexity, the ability to harness energy from their environment and use it to maintain organized molecular structures against the universal tendency toward disorder. These organisms, classified by microbiologists as chemolithotrophic bacteria, derive their energy not from sunlight or organic compounds, but from the chemical bonds present in dissolved minerals and gases that permeate the early ocean system. Hydrogen sulfide gas, bubbling continuously from underwater volcanic vents, serves as the primary energy source for these primitive metabolic systems. The bacteria oxidize hydrogen sulfide using dissolved iron compounds as electron acceptors, a chemical reaction that releases modest quantities of energy while producing elemental sulfur as a metabolic waste product. This process, known as chemosynthesis, operates with thermodynamic efficiency far below that of the photosynthetic and respiratory processes that will eventually evolve, yet it provides sufficient energy to support the basic cellular functions necessary for growth and reproduction. The iron-rich chemistry of the early oceans proves ideally suited for these primitive metabolic pathways, as dissolved iron exists in multiple oxidation states that can serve as electron donors and acceptors in the complex chain of chemical reactions that convert environmental energy into cellular energy. Ion cycling becomes the fundamental currency of early biochemistry, with bacterial metabolism driving the transformation of dissolved iron between ferrous and ferric states in patterns that will eventually create some of Earth's most distinctive geological formations. These early bacteria possess cellular structures of remarkable simplicity compared to modern organisms. Lacking the membrane-bound organelles and complex genetic regulatory systems that characterize contemporary life, their genetic material floats freely within the cellular interior, unprotected by nuclear membranes, while their metabolic machinery operates through primitive enzymatic systems that accomplish essential biochemical transformations with minimal molecular complexity. Yet even these simple organisms demonstrate the capacity for exponential population growth when environmental conditions favor their particular metabolic requirements. The waste products of bacterial metabolism begin to accumulate in the ocean system as these primitive organisms multiply across geological timescales. Elemental sulfur precipitates from solution where bacterial hydrogen sulfide oxidation occurs in concentrated patches, creating the first biological sediments in Earth's geological record. More significantly, the oxidation of dissolved iron by bacterial metabolism removes iron from solution and deposits it as iron oxide minerals on the ocean floor, beginning the process that will eventually create the banded iron formations that characterize Archean geology. The timescales involved in these early biological processes stretch across hundreds of millions of years, as bacterial populations expand and contract in response to fluctuations in volcanic activity, ocean chemistry, and global climate conditions. Individual bacterial generation times likely exceed those of modern bacteria by factors of 10 or more due to the extreme chemical conditions and limited energy availability that characterize the early ocean environment. Population growth proceeds with the patience of geological processes, doubling times measured in decades rather than the hours or days typical of contemporary bacterial reproduction. Temperature tolerance among these primitive organisms extends far beyond the range that will eventually constrain biological activity, with some species thriving in waters approaching the boiling point of pure water under standard atmospheric pressure. This thermophilic adaptation reflects the high temperature conditions that prevail throughout the early ocean system and suggests that life's first experiments with cellular organization occurred under environmental conditions that would prove instantly lethal to most modern organisms. The geographical distribution of these early bacterial communities follows patterns determined entirely by chemical gradients and energy availability, rather than the complex ecological interactions that will eventually shape biological communities. Dense bacterial populations develop around underwater volcanic vents, where hydrogen sulfide concentrations reach optimal levels for chemosynthetic metabolism, while vast areas of the ocean remain essentially sterile due to chemical conditions that cannot support even the most primitive metabolic processes. Genetic exchange among these early bacteria occurs through horizontal transfer mechanisms that allow direct sharing of genetic material between individual cells without the sexual reproduction processes that will eventually evolve in more complex organisms. This lateral gene transfer accelerates evolutionary adaptation by allowing beneficial genetic innovations to spread rapidly through bacterial populations, creating a form of collective genetic intelligence that enables rapid response to changing environmental conditions. The chemical signatures of early bacterial metabolism begin to appear in the sedimentary record as distinctive isotopic ratios that reflect the preferential utilization of lighter carbon and sulfur isotopes by biological processes. These biosignatures provide paleontologists with evidence of bacterial activity in rocks that formed billions of years ago, creating a fossil record of metabolism that predates the preservation of actual cellular structures by hundreds of millions of years. Competition between different bacterial species for limited chemical resources drives the first evolutionary pressures toward metabolic efficiency and environmental adaptation. Bacterial strains that can extract energy more effectively from available chemical substrates gradually replace less efficient competitors through natural selection operating on time scales that span millions of years. This slow evolutionary optimization of metabolic pathways establishes the foundation for the biochemical diversity that will eventually characterize life on Earth. The accumulation of metabolic waste products from bacterial activity begins to alter ocean chemistry in ways that will have profound consequences for the planet's future evolution. The gradual removal of dissolved iron from seawater through bacterial oxidation processes reduces the chemical buffering capacity of the ocean system, making it more susceptible to dramatic chemical changes when new metabolic pathways eventually evolve. The stage is set for the emergence of photosynthesis and the resulting transformation of Earth's atmosphere from its current reducing chemistry toward the oxidizing conditions that will eventually support complex multicellular life. The invisible architects of this transformation work with molecular tools and energy sources that will become obsolete as Earth's chemistry evolves toward more oxidized conditions. Yet their metabolic innovations establish the biochemical foundation upon which all future life will build. In the chemical darkness of the early oceans, bacteria begin the 4 billion-year project of transforming a sterile planet into a world capable of supporting the complexity and consciousness that will eventually contemplate their own origins in these ancient and alien seas. The first molecules of free oxygen to appear in Earth's oceans emerge as an accidental byproduct of bacterial experimentation with a new form of metabolism that harnesses the energy of sunlight rather than the chemical bonds of dissolved minerals. These pioneering cyanobacteria, among the first organisms to develop the complex molecular machinery necessary for photosynthesis, begin splitting water molecules to extract electrons for their metabolic processes, releasing oxygen gas as an unwanted waste product that will eventually transform every aspect of Earth's surface chemistry. The photosynthetic process operates through a series of chemical reactions so intricate that their evolution represents one of the most remarkable achievements in the history of molecular engineering. Specialized protein complexes embedded in bacterial cell membranes capture photons of sunlight and use their energy to drive electrons through a chain of chemical reactions that ultimately produce organic compounds from carbon dioxide and water. The process requires the precise coordination of dozens of different enzymes and cofactors, each contributing specific chemical capabilities to the overall transformation of light energy into biological energy. Initially, these oxygen-producing bacteria represent only a tiny fraction of the total bacterial population in the early oceans, confined to shallow coastal waters where sunlight penetration reaches sufficient intensity to drive photosynthetic metabolism. The vast majority of bacterial life continues to depend on chemosynthetic processes that utilize the dissolved chemicals abundant in the iron-rich ocean system. The oxygen produced by these early photosynthetic communities dissolves immediately into the surrounding seawater, where it reacts with dissolved iron to form insoluble iron oxide compounds that precipitate onto the ocean floor. This precipitation process creates the first banded iron formations, geological structures that consist of alternating layers of iron-rich and iron-poor sediments deposited over millions of years as bacterial oxygen production fluctuates with changes in population size and environmental conditions. These formations, some of which extend for hundreds of kilometers and reach thicknesses of several hundred meters, represent the most direct geological evidence of early photosynthetic activity and provide a detailed record of oxygen production rates during the first billion years of biological evolution. The chemical toxicity of oxygen to the anaerobic bacteria that dominate early ocean ecosystems creates the first global environmental crisis in Earth's biological history. Oxygen readily reacts with the sulfur-containing amino acids and iron-sulfur clusters that form essential components of primitive cellular machinery, disrupting metabolic processes and causing widespread bacterial mortality in regions where oxygen concentrations exceed the tolerance limits of anaerobic organisms. This phenomenon, which paleobiologists term the Great Oxygenation Event, represents the first mass extinction in Earth's history, eliminating entire lineages of bacteria that prove unable to adapt to the changing chemical conditions. The gradual accumulation of oxygen in seawater proceeds with the characteristic patience of geological processes, increasing from concentrations measured in parts per billion to parts per million over hundreds of millions of years. This slow rate of change reflects the enormous capacity of dissolved iron and other reduced compounds in the early oceans to consume oxygen through chemical reactions that prevent the gas from accumulating in significant concentrations until these chemical buffers become exhausted through continued photosynthetic production. Bacterial adaptation to oxygen toxicity drives the evolution of new metabolic pathways that can utilize oxygen as an electron acceptor in cellular respiration, transforming this toxic waste product into the foundation of a more efficient energy production system. Aerobic respiration yields approximately 18 times more energy per glucose molecule than the fermentation processes that characterize anaerobic metabolism, providing organisms that develop oxygen tolerance with tremendous competitive advantages in environments where both oxygen and organic compounds are available. The geographical distribution of oxygen in the early ocean system creates a complex three-dimensional mosaic of chemical environments, with high oxygen concentrations near the surface where photosynthetic bacteria thrive, and low oxygen zones in deeper waters where anaerobic communities persist in chemical refugia. This stratification establishes the first clear ecological zonation in Earth's biosphere, as different bacterial communities specialize for survival in specific chemical niches defined by oxygen availability and other environmental factors. The iron oxide minerals formed through bacterial oxygen production accumulate in sedimentary deposits that eventually become some of Earth's most economically important ore bodies, containing iron concentrations that exceed 90% by weight in some formations. The mining of these ancient bacterial waste products provides much of the iron ore that supports modern industrial civilization, creating an economic connection between contemporary technology and the metabolic processes of bacteria that lived billions of years ago. Atmospheric oxygen concentrations remain negligible during the early stages of photosynthetic evolution, as virtually all oxygen production is immediately consumed by chemical reactions with dissolved iron and other reduced compounds in the ocean system. The transition from an oxygen-free atmosphere to detectable atmospheric oxygen concentrations requires the near-complete oxidation of the dissolved iron reservoir, a process that spans several 100 million years and consumes quantities of oxygen equivalent to multiple times the mass of the modern atmosphere. The chemical transformation of seawater from reducing to oxidizing conditions has profound effects on the solubility and bioavailability of trace metals essential for biological processes. Elements such as molybdenum, copper, and zinc become more readily available in oxidized seawater, enabling the evolution of new enzymatic systems that utilize these metals as cofactors in biochemical reactions. Conversely, iron becomes much less soluble in oxygenated water, creating the first biological iron limitation and driving the evolution of sophisticated iron acquisition systems in marine bacteria. The development of cellular mechanisms for managing oxygen toxicity leads to the evolution of antioxidant enzyme systems that neutralize reactive oxygen species before they can damage cellular components. These protective mechanisms, including catalase and superoxide dismutase enzymes, become essential components of all aerobic life forms and represent some of the most highly conserved biochemical systems in modern biology, unchanged in their fundamental structure across billions of years of evolutionary time. The coevolution of oxygen production and oxygen consumption establishes the first biological feedback loops that regulate atmospheric and oceanic chemistry through the collective metabolic activity of countless individual organisms. As photosynthetic bacteria increase oxygen production, they create environmental conditions that favor the evolution and expansion of aerobic bacteria, which in turn consume oxygen through respiratory metabolism, preventing unlimited accumulation of this reactive gas in Earth's surface environments. The fossil record of this transition period preserves evidence of the first biological arms race, as bacterial lineages develop increasingly sophisticated mechanisms for either avoiding oxygen toxicity or exploiting oxygen for metabolic advantage. The evolutionary pressure created by changing ocean chemistry accelerates the rate of biological innovation, driving the development of new metabolic pathways, cellular structures, and biochemical systems that will provide the foundation for all subsequent biological evolution. As the Great Oxygenation Event approaches its culmination with the exhaustion of dissolved iron buffers in the ocean system, Earth stands poised for the next major transition in its biological evolution, the emergence of atmospheric oxygen and the transformation of the planet's surface from a reducing environment dominated by anaerobic life to an oxidizing world where aerobic metabolism can support the energy demands of increasingly complex forms of life. When atmospheric oxygen finally begins to accumulate after hundreds of millions of years of oceanic ion oxidation, Earth's climate system responds with a transition so dramatic that it transforms the planet from a warm, greenhouse world into a frozen sphere where ice sheets advance from both polar regions toward the equator with relentless persistence. This phenomenon, which geologists term snowball Earth, represents the most extreme climate event in the planet's history, creating global ice coverage so complete that even tropical oceans freeze solid beneath ice sheets several kilometers thick. The mechanism that triggers this dramatic climate transition involves the chemical interaction between atmospheric oxygen and methane, a greenhouse gas that has helped maintain Earth's warm temperatures throughout the Archean and early Proterozoic eons. As oxygen concentrations rise above critical threshold levels, atmospheric methane undergoes rapid oxidation to carbon dioxide and water vapor, eliminating a greenhouse gas with warming potential 25 times greater than carbon dioxide. The resulting reduction in atmospheric greenhouse effect allows Earth's surface temperature to drop below the freezing point of seawater across most of the planet's surface. The initial formation of sea ice creates a positive feedback mechanism that accelerates the cooling process through increased reflection of solar radiation back to space. Fresh ice reflects approximately 90% of incident sunlight, compared to the 10% reflection of dark ocean water, dramatically reducing the amount of solar energy absorbed by Earth's surface. As ice coverage expands, this albedo effect becomes increasingly powerful, driving surface temperatures even lower and promoting further ice formation in a runaway cooling process that continues until the entire planet achieves ice coverage. The advance of ice sheets across the continental surfaces proceeds with the inexorable persistence of gravitational flow, as accumulated snow compresses into glacial ice that spreads outward from polar regions under its own weight. These ice sheets reach thicknesses exceeding 3 kilometers in some regions, creating ice loads sufficient to depress the underlying crustal rock by hundreds of meters through isostatic adjustment. The weight of continental ice sheets alters global sea level by storing vast quantities of water in solid form, exposing continental shelves and creating land bridges between previously separated land masses. Ocean circulation beneath the global ice cover operates according to entirely different principles than the wind-driven surface currents that characterize ice-free marine systems. Convection currents driven by temperature and salinity differences transport heat and dissolved chemicals through the water column in patterns that remain largely isolated from atmospheric influence. These deep circulation systems maintain liquid water beneath the ice through the combined effects of pressure, salinity, and geothermal heating from underwater volcanic activity. The biological consequences of global glaciation prove catastrophic for most forms of life that have evolved to depend on liquid water and moderate temperatures for their metabolic processes. Photosynthetic bacteria, which require liquid water and sunlight for their energy production, face near extinction as ice coverage eliminates the shallow marine environments where these organisms have thrived for hundreds of millions of years. The few surviving photosynthetic communities persist in isolated refugia around underwater volcanic vents or in temporary melt pools created by geothermal activity. Atmospheric composition during the snowball Earth episodes differs dramatically from both earlier and later periods in Earth's history, with oxygen concentrations remaining relatively low due to the near cessation of photosynthetic production, while carbon dioxide levels gradually increase through continued volcanic outgassing that cannot be balanced by biological consumption or chemical weathering of exposed rock surfaces. This slow accumulation of atmospheric carbon dioxide eventually provides the greenhouse warming necessary to escape from the global glaciation. The duration of individual snowball Earth episodes spans tens of millions of years, periods so extended that they encompass hundreds of thousands of generations even for long-lived organisms. During these frozen epochs, evolution continues in the isolated liquid water environments that persist beneath the ice. But the severe environmental constraints limit biological innovation and maintain most life forms in survival mode rather than promoting the development of new metabolic capabilities or structural complexity. Geological evidence for these extreme glaciation events appears in rock formations from every continent, where glacial deposits of clearly tropical origin indicate ice coverage at latitudes that currently experience year-round temperatures well above freezing. Dropstones, large rocks carried by icebergs and deposited in fine-grained marine sediments, occur in sedimentary sequences that formed at equatorial latitudes, providing compelling evidence that floating ice existed even in the warmest regions of the ancient Earth. The escape from snowball Earth conditions requires the accumulation of atmospheric carbon dioxide concentrations hundreds of times higher than modern levels. As volcanic outgassing continues throughout the frozen periods, while biological and chemical consumption of carbon dioxide remains minimal due to the absence of liquid water on most of the planet's surface. This extreme greenhouse effect eventually overcomes the cooling influence of global ice coverage, triggering rapid deglaciation that transforms the planet from a frozen world to a greenhouse climate within a few thousand years. The rapidity of deglaciation creates environmental conditions even more extreme than the initial cooling, as the sudden melting of continental ice sheets releases enormous quantities of fresh water into the ocean system, while simultaneously exposing vast areas of previously frozen land to intense solar radiation and high atmospheric carbon dioxide concentrations. Surface temperatures during these deglaciation events likely exceed modern tropical temperatures by tens of degrees, creating a briefly hyper-greenhouse climate before atmospheric carbon dioxide levels decline through enhanced weathering and renewed biological activity. Chemical weathering processes accelerate dramatically during the post-glacial warming periods, as high temperatures and carbon dioxide concentrations promote rapid dissolution of exposed rock surfaces by carbonic acid solutions. This enhanced weathering consumes atmospheric carbon dioxide at rates that exceed volcanic production, gradually returning Earth's climate to more moderate conditions suitable for the recovery and diversification of biological communities that survive the glacial episodes in their deep water refugia. The repeated cycles of global glaciation and deglaciation that characterize the late Proterozoic eon create severe evolutionary bottlenecks that eliminate most existing bacterial lineages while simultaneously creating opportunities for rapid diversification among the survivors. These dramatic environmental oscillations may have provided the evolutionary pressure necessary for the development of more complex cellular structures and multicellular organization, as simple bacterial communities prove vulnerable to extinction during the extreme climate transitions. Ocean chemistry undergoes profound changes during each glaciation cycle, as the cessation of photosynthetic oxygen production allows dissolved iron concentrations to increase, while the isolation of marine environments beneath ice coverage creates locally anoxic conditions that favor different metabolic pathways than those that operate in oxygenated surface waters. These chemical fluctuations create a complex mosaic of environmental conditions that may have promoted the evolution of metabolic flexibility and environmental tolerance among surviving organisms. The Snowball Earth episodes represent perhaps the closest Earth has ever approached to complete biological extinction, yet they also establish the conditions that will eventually enable the evolution of complex multicellular life forms. The environmental extremes created by global glaciation eliminate most simple bacterial communities while providing evolutionary opportunities for the few lineages that develop sufficient complexity to survive dramatic environmental transitions, setting the stage for the biological innovations that will eventually lead to the emergence of animals, plants, and the complex ecosystems that characterize modern Earth. In the aftermath of the final Snowball Earth deglaciation, as global temperatures stabilize and liquid oceans once again extend from pole to pole, the solid foundation beneath these recovering seas begins a slow dance of fragmentation and collision that will reshape the planet's surface geography over hundreds of millions of years. The continental masses that emerge from the ice as single, coherent landforms start to fracture along lines of geological weakness, creating rifts that gradually widen into seaways and eventually into full ocean basins that separate the fragments across thousands of kilometers of open water. The driving force behind this continental breakup originates deep within Earth's interior, where convection currents in the molten mantle create ascending plumes of hot rock that rise toward the surface like bubbles in a viscous liquid. When these mantle plumes encounter the base of the continental crust, they spread laterally beneath the solid rock, creating thermal domes that stretch and thin the overlying crustal materials until they fracture under the accumulated stress. The fractures begin as narrow valleys that gradually deepen and widen, as continued extension pulls the continental fragments apart, with forces measured in millions of tons per square kilometer. The initial stages of continental rifting proceed with geological patience, as crustal extension rates rarely exceed a few centimeters per year, slower than the growth of human fingernails. Yet inexorable when sustained across millions of years, the rift valleys that form during these early stages resemble the modern East African rift system, with steep escarpments rising hundreds of meters above sunken central valleys, where volcanic activity creates new crustal material to fill the gaps created by crustal extension. These ancient rift systems preserve evidence of Earth's first experiments with the tectonic processes that will eventually become plate tectonics. As rifting continues and the continental fragments separate beyond the point where they can maintain crustal continuity, seawater floods into the expanding gaps, creating narrow seaways that gradually evolve into full ocean basins as seafloor, spreading processes begin to operate along the rift axes. The chemistry of these early seaways differs significantly from that of the main ocean basins, as restricted circulation creates conditions where evaporation can concentrate dissolved salts to levels that exceed the saturation point of various mineral compounds, creating extensive evaporate deposits that preserve chemical records of early ocean composition. The fragments of continental crust that separate during these rifting events begin their slow journey across Earth's surface, carried by the movement of underlying mantle convection cells that transport them at velocities comparable to the growth rate of human hair. These ancient continental plates follow curved trajectories across the planet's spherical surface, sometimes approaching each other again after hundreds of millions of years of separation to create collision zones where the continental margins crumple and fold into mountain ranges that rival the modern Himalayas in their scale and complexity. The first supercontinent to form through this process of fragmentation and reassembly aggregates approximately 1 billion years ago, bringing together continental fragments that have been separated for hundreds of millions of years during their individual journeys around the globe. This massive landmass, which geologists have named Rodinia after the Russian word for homeland, extends from polar regions to tropical latitudes and encompasses nearly all of Earth's continental crust in a single coherent structure that profoundly influences global climate and ocean circulation patterns. The formation of Rodinia creates climate conditions unlike anything in Earth's earlier history, as the assembly of continental masses into a single supercontinent eliminates many of the seaways that previously moderated global temperatures through oceanic heat transport. The interior regions of the supercontinent experience extreme continental climate conditions, with temperature variations between summer and winter that exceed anything experienced in modern continental interiors. The vast size of Rodinia also creates orographic effects that influence precipitation patterns across the entire landmass, creating desert conditions in some regions while concentrating rainfall in narrow coastal zones. Ocean circulation around the supercontinent operates according to entirely different principles than the complex current systems that characterize modern oceans with their multiple continental barriers and narrow seaways. The single massive ocean that surrounds Rodinia, known as the Panthalassic Ocean, develops circulation patterns of unprecedented scale and intensity, creating western and eastern boundary currents that transport heat and dissolved chemicals across distances that span entire hemispheres. These oceanic circulation systems operate with such efficiency that they homogenize ocean chemistry and temperature to degrees unknown in modern marine systems. The biological consequences of supercontinent formation prove profound for the evolution of life on Earth, as the reduced coastal habitat and simplified ocean circulation eliminate many of the environmental niches that have supported biological diversity during earlier periods of continental fragmentation. The concentration of continental area into a single landmass reduces the total length of coastline where marine and terrestrial environments interact, limiting opportunities for the evolution of organisms adapted to transitional environmental conditions that will eventually become crucial for the colonization of land by marine life forms. Volcanic activity associated with supercontinent assembly creates massive igneous provinces where mantle plumes breach the continental crust and flood vast areas with basaltic lava flows that can exceed 1 million square kilometers in extent. These large igneous provinces represent some of the most dramatic volcanic events in Earth's history, releasing quantities of volcanic gases sufficient to alter global atmospheric composition and triggering climate changes that affect biological communities across the entire planet. The timing of these volcanic episodes often coincides with mass extinction events, suggesting causal relationships between tectonic processes and biological evolution. The breakup of Rodinia begins approximately 750 million years ago, as new mantle plumes develop beneath the supercontinent and begin the process of rifting that will eventually separate the continental fragments once again. This breakup process proves even more complex than the original assembly, as the supercontinent fractures along multiple rift systems that develop simultaneously across different regions of the landmass. The resulting fragmentation creates a complex arrangement of continental blocks and ocean basins that establishes the geographical foundation for the biological innovations that will characterize the later Precambrian and early Paleozoic eras. The opening of new ocean basins during Rodinia's breakup creates opportunities for biological innovation and diversification, as increased coastal habitat and more complex ocean circulation patterns generate environmental conditions that favor the evolution of more complex life forms. The chemical changes associated with enhanced oceanic mixing and increased weathering rates provide new sources of nutrients and trace metals that enable the development of more sophisticated biochemical systems, including the cellular machinery necessary for multicellular organization and sexual reproduction. Sedimentary deposits associated with the Rodinian supercontinent cycle preserve detailed records of environmental conditions during this crucial period of Earth's history, including evidence for dramatic climate changes, massive volcanic eruptions, and the first appearances of complex multicellular organisms in the fossil record. These geological archives provide paleontologists with insights into the relationships between tectonic processes and biological evolution, demonstrating the fundamental importance of plate tectonics for creating the environmental conditions necessary for the development of complex life on Earth. The legacy of the Rodinian supercontinent cycle establishes many of the geological and geographical patterns that will influence Earth's subsequent evolution, including the distribution of mineral resources, the configuration of major mountain ranges, and the arrangement of continental masses that will control climate and ocean circulation patterns for hundreds of millions of years into the future. The slow dance of continental assembly and fragmentation continues to operate according to the same fundamental principles established during this early supercontinent cycle, driving the ongoing geological evolution that shapes Earth's surface environments and influences the evolutionary trajectories of all life forms that depend on the planet's dynamic crustal processes. Within the chemical depths of Proterozoic oceans, where dissolved nutrients circulate in patterns established by the slow fragmentation of the supercontinent Rodinia, individual bacterial cells begin the most consequential biological experiment in Earth's history: the merger of separate cellular lineages into composite organisms that function as integrated wholes rather than competing individuals. This process, which evolutionary biologists term endosymbiosis, transforms simple bacterial communities into the complex cellular architecture that will eventually enable the evolution of all plants, animals, fungi, and other multicellular organisms. The ancestral participants in this cellular merger represent two fundamentally different approaches to bacterial survival that have evolved independently over hundreds of millions of years. The host bacteria, classified as archaea, possess cellular machinery optimized for survival in extreme chemical environments, including the high temperatures, acidic conditions, and metal-rich waters that characterize many Proterozoic marine habitats. These organisms maintain their genetic material in loose association with specialized proteins, lacking the membrane-bound nucleus that will eventually characterize more complex cells. The bacterial partners that become incorporated into these archaeal hosts belong to lineages that have developed sophisticated metabolic capabilities, including the oxygen-utilizing respiratory pathways that can extract energy from organic compounds with efficiency far exceeding that of fermentation-based metabolism. These aerobic bacteria possess cellular machinery capable of managing the toxic effects of oxygen while harnessing its chemical reactivity to power energy production systems that yield 18 times more cellular energy per glucose molecule than anaerobic alternatives. The initial encounters between these distinct bacterial lineages likely occur through predatory interactions, as larger archaeal cells attempt to consume smaller aerobic bacteria by engulfing them through primitive phagocytic processes. However, instead of digesting their bacterial prey, Some archaeal cells develop the capacity to maintain living bacteria within their cellular interior, creating composite organisms where the internal bacteria continue their metabolic activities while receiving protection and nutrients from their archaeal hosts. This symbiotic arrangement proves advantageous for both cellular partners, as the host archaea gain access to the highly efficient aerobic metabolism of their internal bacteria, while the bacterial symbionts benefit from the chemical buffering and nutrient concentration capabilities of their archaeal hosts. The evolutionary success of these composite organisms becomes apparent through their rapid population growth in environments where oxygen availability makes aerobic metabolism advantageous, particularly in the shallow marine waters where photosynthetic bacteria maintain oxygen concentrations sufficient to support respiratory processes. Over millions of years of coevolution, the bacterial symbionts gradually lose many of the cellular functions that become unnecessary within the protected environment of their archaeal hosts. Genes responsible for cell wall synthesis, nutrient acquisition, and environmental sensing transfer from the bacterial genome to the host genome through horizontal gene transfer processes, creating increasingly integrated cellular systems where the distinction between host and symbiont becomes progressively blurred. The descendants of these ancient bacterial symbionts persist in modern eukaryotic cells as mitochondria, the membrane-bound organelles responsible for aerobic respiration in all animals, plants, fungi, and most other complex organisms. Mitochondrial DNA sequences preserve evidence of their bacterial origins, showing clear evolutionary relationships to free-living aerobic bacteria while displaying the reduced genome size characteristic of organisms that have evolved within symbiotic relationships for extended periods. A second endosymbiotic event, involving the incorporation of photosynthetic cyanobacteria into early eukaryotic cells, creates the lineage that will eventually give rise to all plants and algae. These photosynthetic symbionts, which evolve into the chloroplasts of modern plant cells, provide their hosts with the capability to harness solar energy for organic compound synthesis, enabling the evolution of organisms that can survive independently of external organic carbon sources through photosynthetic metabolism. The development of membrane-bound organelles through endosymbiosis enables the evolution of much larger cell sizes than those achievable by simple bacterial cells, as the compartmentalization of cellular functions allows more efficient organization of metabolic processes and genetic regulation. Early eukaryotic cells reach sizes hundreds of times larger than their bacterial ancestors, creating opportunities for the development of more complex cellular structures and biochemical systems that require spatial organization beyond the capabilities of simple bacterial architecture. The evolution of sexual reproduction among these early eukaryotic organisms creates genetic mixing processes that accelerate evolutionary adaptation beyond the rates achievable through the horizontal gene transfer mechanisms that characterize bacterial evolution. Sexual reproduction enables the rapid combination of beneficial genetic variations from different individual organisms, creating offspring with genetic combinations that may prove advantageous in changing environmental conditions while maintaining genetic diversity within populations. Cellular division processes in early eukaryotic organisms develop the complex mitotic machinery necessary to ensure accurate distribution of genetic material and organelles to daughter cells during reproduction. This sophisticated cellular apparatus requires the coordinated function of hundreds of different proteins organized into structures such as chromosomes, spindle fibers, and nuclear membranes that have no equivalents in bacterial cellular organization, representing entirely new innovations in cellular architecture. The metabolic capabilities of early eukaryotic cells exceed those of their bacterial ancestors by orders of magnitude, as the combination of multiple organelle energy production systems enables cellular energy budgets sufficient to support active locomotion, complex behavioral responses, and the synthesis of elaborate cellular structures. These enhanced metabolic capabilities provide the energetic foundation necessary for the evolution of predatory lifestyles, sexual reproduction, and other energy-intensive biological processes. The fossil record of early eukaryotic evolution preserves evidence of the first organisms large enough to be visible without microscopic magnification, including cells with complex internal structures that reflect the sophisticated cellular organization made possible by endosymbiotic organelle acquisition. These fossils, dating to approximately 1.5 billion years ago, demonstrate that the fundamental cellular architecture characterizing modern complex life had evolved by the Middle Proterozoic eon. Environmental conditions during the period of eukaryotic evolution favor the success of these metabolically sophisticated organisms, as increasing atmospheric oxygen concentrations create widespread marine environments where aerobic metabolism provides competitive advantages over anaerobic alternatives. The geographic distribution of early eukaryotic fossils suggests that these organisms initially evolved in shallow marine environments where oxygen availability, nutrient concentrations, and solar radiation levels optimize the metabolic capabilities provided by their endosymbiotic organelles. The evolutionary success of early eukaryotic organisms establishes the cellular foundation upon which all subsequent biological complexity will build. As the metabolic capabilities, genetic organization, and reproductive mechanisms developed through endosymbiotic cellular merger provide the necessary prerequisites for the evolution of multicellular organization, tissue differentiation, and the complex organ systems that will eventually characterize plants, animals, and other macroscopic life forms. The legacy of these ancient endosymbiotic partnerships persists in every complex cell on Earth today. As mitochondria and chloroplasts continue to function according to the same basic metabolic principles established billions of years ago through the merger of separate bacterial lineages. The cellular cooperation that begins with these early endosymbiotic relationships establishes cooperation as a fundamental principle of biological organization, demonstrating that evolutionary success often results from mutualistic partnerships rather than competitive exclusion between different forms of life. For nearly 3 billion years after the emergence of the first eukaryotic cells with their sophisticated organella architecture, life on Earth maintains a microscopic existence that betrays no hint of the explosive diversification that will eventually transform the planet's biosphere beyond recognition. Individual cells drift through the ancient oceans as solitary entities, each organism complete unto itself, carrying out the fundamental processes of metabolism, growth, and reproduction within the confines of cellular membranes that define the boundaries between self and environment with molecular precision. The transition from this microscopic world to the complex multicellular organisms that will eventually populate land and sea requires evolutionary innovations so profound that they represent discontinuities in the history of life as dramatic as any technological revolution in human civilization. The first tentative experiments with multicellular organization begin not through the evolution of new cellular types, but through the simple failure of daughter cells to separate completely following cellular division, creating colonies of genetically identical individuals that remain physically connected through cellular bridges or shared extracellular matrices. These early colonial organisms resemble modern algae and bacterial mats more than the complex animals that will eventually evolve from their multicellular experiments. Yet they establish the fundamental principle that individual cells can sacrifice some degree of independence to gain advantages available only through cooperative behavior. Colonial cells can achieve larger sizes than solitary individuals, creating opportunities for more efficient nutrient capture, enhanced protection against environmental stresses, and improved reproductive success through coordinated cellular activities. The evolutionary transition from simple cell colonies to true multicellular organisms requires the development of cellular differentiation, the process by which genetically identical cells develop distinct structural and functional characteristics that enable specialized roles within the multicellular community. This cellular specialization demands sophisticated gene regulation mechanisms that can activate different sets of genes in different cells despite their shared genetic heritage, creating the molecular machinery necessary for building organisms composed of multiple cell types. The first evidence of complex multicellular organisms appears in the fossil record approximately 600 million years ago, in geological formations that preserve the impressions of soft-bodied creatures unlike anything that existed during the preceding 3 billion years of life's history. These organisms, known collectively as the Ediacaran biota after the Australian hills where they were first discovered, display body plans and organizational complexity that represent quantum leaps beyond the simple colonial forms that characterize earlier multicellular experiments. The Ediacaran organisms achieve body sizes measured in centimeters and even meters, creating the first macroscopic life forms capable of visible modification of their seafloor environments through feeding, locomotion, and construction activities. These ancient creatures display radial and bilateral symmetries that suggest sophisticated developmental programs capable of organizing cellular growth and differentiation into predictable anatomical patterns, indicating the evolution of genetic regulatory networks complex enough to control multicellular development. The feeding strategies of Ediacaran organisms remain enigmatic to paleontologists, as many species lack obvious mouth openings, digestive cavities, or other anatomical features associated with conventional feeding mechanisms. Some researchers propose that these early multicellular organisms maintained symbiotic relationships with photosynthetic bacteria, obtaining nutrition through internal cultivation of microbial partners rather than through direct consumption of external food sources, a strategy that would parallel the endosymbiotic relationships that gave rise to chloroplasts in plant cells. The ocean chemistry during the Ediacaran period creates environmental conditions that favor the evolution of large, complex organisms through the availability of dissolved nutrients and trace metals essential for sophisticated biochemical processes. Increased weathering rates associated with continental fragmentation and mountain building deliver elevated concentrations of phosphorus, nitrogen, and iron to marine environments, supporting higher levels of biological productivity and enabling the metabolic demands of multicellular organization. Atmospheric oxygen concentrations during the Ediacaran period reach levels approaching modern atmospheric composition for the first time in Earth's history, providing the energetic foundation necessary for the active lifestyles and complex developmental processes that characterize early multicellular animals. The availability of abundant atmospheric oxygen enables aerobic metabolism at scales sufficient to support the energy demands of locomotion, sensory processing, and other activities that require metabolic rates far exceeding those achievable through anaerobic biochemical pathways. The geographical distribution of Ediacaran fossils spans multiple continents and marine environments, indicating that multicellular complexity evolves rapidly once the fundamental innovations of cellular differentiation and tissue organization become established in early animal lineages. The global occurrence of similar body plans and organizational strategies suggests that the evolutionary transition to multicellularity follows predictable developmental pathways that reflect universal constraints on biological organization and environmental adaptation. The extinction of most Ediacaran organisms at the end of the Precambrian era creates paleontological mysteries that continue to challenge researchers attempting to understand the relationship between these early multicellular experiments and the more familiar animal forms that appeared during the subsequent Cambrian explosion. The anatomical organization of Ediacaran creatures displays few obvious evolutionary connections to later animal phyla, suggesting either complete extinction of these early lineages or radical evolutionary reorganization during the transition to Phanerozoic life. The developmental mechanisms that enable Ediacaran multicellularity require the evolution of cell-cell communication systems that allow individual cells to coordinate their activities and respond to signals from neighboring cells within the multicellular community. These intercellular signaling pathways utilize chemical messengers that can diffuse between cells or travel through specialized cellular connections, creating information networks that enable multicellular organisms to function as integrated wholes rather than collections of independent cellular entities. The evolution of extracellular matrices during the Ediacaran period provides multicellular organisms with structural support systems that enable the maintenance of complex three-dimensional body plans while allowing controlled flexibility for locomotion and environmental interaction. These extracellular materials, composed of proteins and polysaccharides secreted by specialized cells, create scaffolding systems that support cellular organization while providing protection against mechanical damage and environmental stresses. Sexual reproduction becomes increasingly sophisticated among Ediacaran organisms, with some species displaying evidence of complex life cycles that include both sexual and asexual reproductive phases, enabling rapid population growth during favorable environmental conditions while maintaining genetic diversity through sexual genetic recombination. These reproductive innovations provide early multicellular organisms with evolutionary flexibility that proves crucial for adaptation to the changing environmental conditions that characterize the late Precambrian period. The biomechanical innovations that enable Ediacaran locomotion include the development of muscular tissues capable of coordinated contraction and relaxation, creating the first animal movements more sophisticated than the simple cellular motility that characterizes earlier life forms. These early locomotory systems enable active foraging, predator avoidance, and habitat selection behaviors that represent the beginning of the complex ecological interactions that will eventually characterize animal communities throughout Earth's subsequent biological evolution. The legacy of Ediacaran multicellular innovation establishes the organizational principles and developmental mechanisms that will provide the foundation for all subsequent animal evolution, creating the biological architecture upon which the Cambrian explosion will build the diverse animal phyla that continue to dominate modern ecosystems nearly 600 million years after these first experiments with complex multicellular life began their transformation of Earth from a microbial world into the macroscopic biosphere we inhabit today. While the first tentative multicellular animals explore their possibilities in the ancient oceans, entirely different evolutionary experiments unfold in the marginal zones, where water meets the barren continental surfaces that have remained devoid of life throughout Earth's entire biological history. Here, in the chemical transition zones between marine and terrestrial environments, primitive algae and cyanobacteria begin the monumental task of biological colonization that will eventually transform the sterile landscapes of the Proterozoic continents into the verdant terrestrial ecosystems that will support the evolution of land animals hundreds of millions of years in the future. The challenge of terrestrial survival confronts these pioneering organisms with environmental obstacles that have no equivalent in the aquatic habitats where life has evolved for more than 3 billion years. The absence of liquid water creates desiccation stresses that can destroy cellular structures within minutes of exposure, while the unfiltered solar radiation that reaches continental surfaces carries ultraviolet wavelengths capable of breaking the chemical bonds that maintain genetic integrity and protein function. The temperature fluctuations between day and night on exposed land surfaces exceed the thermal tolerance ranges of most aquatic organisms, creating environmental extremes that require entirely new physiological adaptations. The first successful terrestrial colonists developed biochemical strategies for managing water loss that enable survival during periods of atmospheric desiccation, while maintaining the cellular hydration necessary for metabolic function. These early land plants evolve specialized cellular structures that can enter dormant states during dry periods, reducing metabolic activity to minimal levels while preserving essential cellular components until moisture becomes available again through precipitation or atmospheric humidity. The ability to survive repeated cycles of hydration and desiccation provides these organisms with competitive advantages in environments where water availability fluctuates unpredictably. Photosynthetic organisms that colonize terrestrial environments gain access to solar radiation intensities that far exceed those available in aquatic habitats, where water absorption and scattering reduce light penetration to levels that limit photosynthetic efficiency. The direct exposure to unfiltered sunlight enables land plants to achieve photosynthetic rates sufficient to support larger body sizes and more complex anatomical structures than those possible for their aquatic ancestors, creating opportunities for evolutionary innovations that will eventually lead to the development of complex plant tissues and organ systems. The absence of aquatic support systems requires terrestrial organisms to develop structural mechanisms that can maintain cellular organization and tissue integrity against the mechanical stresses imposed by gravitational forces and atmospheric turbulence. Early land plants evolve rigid cell walls and supportive tissues that provide structural stability while allowing sufficient flexibility to prevent mechanical damage from wind and temperature fluctuations. These structural innovations represent the first biological experiments with architecture designed specifically for terrestrial environments. Nutrient acquisition poses fundamental challenges for terrestrial organisms, as the essential chemical elements required for biological processes must be extracted from solid mineral substrates rather than dissolved nutrients readily available in aquatic environments. Pioneer land plants develop specialized cellular interfaces that can penetrate rock surfaces and extract dissolved minerals through chemical weathering processes that accelerate the breakdown of crustal materials. These biochemical weathering mechanisms contribute significantly to soil formation processes that will eventually create the chemical foundations for complex terrestrial ecosystems. Reproduction among early terrestrial organisms requires evolutionary innovations that enable genetic material to survive transmission between individuals across dry atmospheric environments rather than through the aquatic media that facilitate reproductive processes in marine organisms. Some early land plants develop resistant spores that can withstand desiccation and temperature extremes while maintaining genetic viability for extended periods, enabling successful reproduction even when environmental conditions prevent immediate germination and growth. The ecological impact of terrestrial plant colonization proves profound for global biogeochemical cycles, as the establishment of photosynthetic communities on continental surfaces creates new pathways for atmospheric carbon dioxide consumption and oxygen production that operate independently of marine biological processes. Terrestrial photosynthesis begins to influence atmospheric composition on scales that will eventually rival the effects of oceanic primary productivity, establishing land-based biological processes as significant factors in global climate regulation. Chemical weathering accelerates dramatically in the presence of terrestrial plant communities, as biological processes enhance the dissolution of crustal minerals through the production of organic acids and the creation of microenvironments where chemical reactions proceed at rates far exceeding those achieved through purely physical weathering mechanisms. This enhanced weathering contributes to atmospheric carbon dioxide removal through the formation of carbonate minerals, while simultaneously releasing essential nutrients that support expanded biological productivity on continental surfaces. The evolution of primitive root systems among early land plants enables more efficient extraction of water and nutrients from soil environments while providing enhanced mechanical stability that allows these organisms to achieve larger sizes and more complex architectural forms. Root development also facilitates deeper penetration of biological processes into crustal materials, expanding the zone of biological influence on geological processes and creating positive feedback mechanisms that accelerate soil formation and ecosystem development. The first terrestrial ecosystems develop around coastal margins and river valleys, where moisture availability remains sufficient to support plant communities during dry seasons, creating biological oases that serve as stepping stones for further inland colonization. These marginal ecosystems establish the ecological templates that will eventually expand across entire continental surfaces as plant communities develop increasingly sophisticated adaptations for surviving in progressively drier and more extreme terrestrial environments. Atmospheric composition changes associated with terrestrial plant evolution include significant increases in oxygen production and carbon dioxide consumption that begin to alter global atmospheric chemistry independently of oceanic biological processes. The development of extensive terrestrial plant communities creates new sources of atmospheric oxygen that will eventually contribute to oxygen concentrations sufficient to support the evolution of complex terrestrial animal communities that depend on aerobic metabolism for their energy requirements. The fossil record preserves evidence of early terrestrial plant communities in geological formations that record the transition from sterile continental surfaces to biologically active terrestrial environments, including fossilized plant materials that demonstrate the anatomical innovations necessary for successful land colonization. These paleobotanical archives provide detailed records of the evolutionary adaptations that enable the transition from aquatic to terrestrial life, documenting one of the most significant ecological transitions in Earth's biological history. Soil development accelerates dramatically following the establishment of terrestrial plant communities, as biological processes contribute organic matter and enhance chemical weathering rates that transform sterile mineral substrates into complex soil systems capable of supporting diverse biological communities. The co-evolution of plants and soils creates positive feedback mechanisms that accelerate ecosystem development and establish the foundations for the complex terrestrial food webs that will eventually support land-animal evolution. The success of early terrestrial plant colonization establishes the biological foundation upon which all subsequent terrestrial evolution will build, creating the oxygen-rich atmospheric conditions, complex soil systems, and diverse plant communities that will eventually enable animals to leave their aquatic origins and colonize the continental surfaces that remain. For now, the exclusive domain of pioneering plants exploring the possibilities of life beyond the boundaries of the ancient seas. The rhythms of life and death that characterize Earth's biological evolution operate according to timescales so vast that individual extinction events unfold across millions of years. Yet, when viewed from the perspective of deep time, these episodes of mass mortality appear as sudden catastrophes that punctuate the planet's biological history, with periods of devastation so complete that they reset the evolutionary trajectory of entire ecosystems. These mass extinction events, occurring approximately once every 26 million years throughout the Phanerozoic eon, eliminate between 70 and 95% of all existing species, creating biological bottlenecks that determine which evolutionary lineages survive to populate the post-extinction world. The most severe of these extinction episodes occurs at the boundary between the Permian and Triassic periods, approximately 252 million years ago, when volcanic eruptions in what is now Siberia release quantities of lava sufficient to cover the continental United States to a depth of several kilometers. These eruptions continue for hundreds of thousands of years, injecting massive quantities of carbon dioxide, sulfur dioxide, and toxic heavy metals into the atmosphere, while simultaneously triggering coal bed combustion that adds even more greenhouse gases to an atmosphere already overwhelmed by volcanic emissions. The environmental consequences of this volcanic catastrophe unfold with the inexorable logic of atmospheric chemistry operating on a global scale. Surface temperatures rise by 10 to 15 degrees Celsius above pre-extinction levels, creating thermal conditions that exceed the physiological tolerance of most marine and terrestrial organisms. Ocean acidity increases to levels that dissolve the calcium carbonate shells of marine invertebrates, while atmospheric hydrogen sulfide concentrations reach toxicity thresholds that poison most air-breathing organisms. The combined effects of these environmental stresses eliminate approximately 96% of marine species and 70% of terrestrial vertebrates. The recovery from this Permian-Triassic extinction requires approximately 10 million years, during which time the few surviving lineages undergo rapid evolutionary radiation to fill the ecological niches left vacant by extinct species. The survivors include small, generalist organisms with broad environmental tolerances and rapid reproductive rates, characteristics that prove crucial for surviving the extreme environmental conditions that persist for millions of years following the initial extinction pulse. These surviving lineages become the ancestors of many modern animal groups, including the Archosaur lineage that will eventually give rise to dinosaurs, crocodiles, and birds. The Cretaceous-Paleogene extinction event that eliminates the non-avian dinosaurs 66 million years ago demonstrates how extraterrestrial impacts can trigger biological catastrophes of comparable magnitude to volcanic mass extinctions. The asteroid that creates the Chicxulub crater in the Yucatan Peninsula releases energy equivalent to billions of nuclear weapons, vaporizing rock and creating a global debris cloud that blocks sunlight for months or years following the impact. The resulting collapse of photosynthetic productivity eliminates the primary food sources that support large herbivorous dinosaurs and the carnivorous species that depend on them. The environmental effects of the Chicxulub impact extend far beyond the immediate destruction caused by the impact itself. As the global debris cloud triggers acid rain, wildfire, and climate cooling that persist for decades following the initial collision, these secondary effects prove more devastating to biological communities than the immediate impact effects, demonstrating how relatively brief extraterrestrial events can trigger environmental cascades that operate on timescales far exceeding the duration of the initial disturbance. The extinction selectivity patterns show that small-bodied organisms with rapid reproductive rates survive preferentially over large-bodied species with slow generation times. The late Devonian extinction events, occurring approximately 375 million years ago, illustrate how gradual environmental changes can produce mass extinction effects comparable to those caused by sudden catastrophic events. Ocean anoxia develops over hundreds of thousands of years as increased nutrient runoff from the newly evolved terrestrial plant communities triggers massive algal blooms that consume atmospheric oxygen when they decompose. The resulting oxygen depletion eliminates most marine organisms that depend on aerobic metabolism, particularly affecting the diverse communities of marine invertebrates that characterize Devonian reef ecosystems. Each mass extinction event creates evolutionary opportunities for surviving lineages by eliminating incumbent species that might otherwise prevent the establishment of new ecological strategies and body plans. The extinction of dominant predators allows previously suppressed herbivorous lineages to undergo adaptive radiation into new ecological niches, while the elimination of competitive exclusion enables the evolution of novel anatomical structures and physiological capabilities that would be selectively disadvantageous in pre-extinction ecosystems. These post-extinction adaptive radiations often produce biological innovations that exceed the complexity and diversity of pre-extinction communities. The fossil record preserves detailed evidence of extinction selectivity patterns that reveal the biological characteristics most crucial for surviving mass extinction events. Small body size, broad environmental tolerance, omnivorous feeding strategies, and rapid reproductive rates emerge as consistent predictors of extinction survival across multiple extinction episodes, while large body size, specialized feeding requirements, and slow reproductive rates correlate strongly with extinction probability. These patterns suggest that generalist organisms possess adaptive advantages during periods of rapid environmental change. The geographic distribution of extinction effects demonstrates that mass extinction events affect global ecosystems unevenly, with some regions experiencing near-complete biological devastation, while others serve as refugia where surviving populations maintain genetic diversity that enables post-extinction recovery. Tropical regions often experience more severe extinction effects than high-latitude areas during climate-related extinction events, while continental interiors may suffer greater losses than coastal regions during impact-related extinctions that affect marine and terrestrial environments differently. The biochemical mechanisms that cause extinction during mass extinction events include direct toxicity from volcanic gases, thermal stress from rapid climate change, starvation from ecosystem collapse, and physiological failure from ocean acidification or atmospheric composition changes. The specific combination of lethal factors varies between different extinction events, but the common thread involves environmental changes that occur too rapidly for evolutionary adaptation to provide effective biological responses to the altered conditions. The role of feedback mechanisms in amplifying extinction effects becomes evident through paleontological analysis of extinction dynamics, as the loss of key species triggers cascading effects that eliminate other species dependent on the extinct organisms for food, habitat, or other ecological services. These ecological cascades can continue for thousands of years after the initial extinction trigger, creating delayed extinction effects that extend the duration of biological crisis far beyond the immediate environmental disturbance that initiated the mass extinction event. The long-term evolutionary consequences of mass extinction events include the elimination of entire evolutionary lineages that represent millions of years of accumulated evolutionary innovation, creating permanent losses of biological complexity that can never be recovered through subsequent evolution. The architectural constraints imposed by surviving body plans limit the range of evolutionary possibilities available to post-extinction communities, channeling biological evolution along trajectories that might never have been explored if different lineages had survived the extinction bottleneck. The mathematical patterns that govern extinction and recovery dynamics suggest that mass extinction events operate as evolutionary reset mechanisms that periodically eliminate accumulated biological complexity and create opportunities for fundamental reorganization of ecosystem structure and function. The time constants for extinction and recovery appear to reflect universal constraints on biological productivity and evolutionary innovation that limit the rate at which complex ecosystems can develop and the speed at which they can recover from catastrophic disruption. The mathematical language that describes geological processes operates according to temporal arithmetic so alien to human experience that it renders the entirety of recorded civilization statistically indistinguishable from instantaneous events when viewed against the backdrop of Earth's 4 billion-year evolutionary timeline. Continental drift proceeds at velocities measured in centimeters per year, yet these microscopic annual movements accumulate across millions of years to transport land masses across thousands of kilometers of planetary surface, opening and closing ocean basins with the patient inevitability of processes that recognize no distinction between geological epochs and human generations. The half-life of uranium-238 decay extends across 47 billion years, a temporal span that encompasses the entire history of Earth from its initial accretion through every geological epoch to the present moment. Individual uranium atoms embedded in crustal rocks undergo radioactive decay according to quantum mechanical probabilities that operate independently of temperature, pressure, chemical environment or any other physical condition that might affect conventional chemical reactions. This radioactive decay provides the planetary heat source that drives plate tectonics, continental drift, and volcanic activity across geological timescales that dwarf the thermal history of stars. Erosion rates in modern mountain ranges average between 10 and 1,000 meters per million years, depending on climate conditions, rock type, and topographical relief. Yet these seemingly modest rates of landscape modification prove sufficient to reduce mountain ranges comparable to the modern Himalayas to sea level within 10 to 100 million years. The Appalachian Mountains, which once rivaled the Himalayas in elevation and extent, have been reduced through erosional processes to their current modest relief over the course of several 100 million years of weathering and mass wasting. The residence time of water molecules in the global ocean system averages approximately 37,000 years, meaning that every drop of seawater currently present in Earth's oceans will cycle through the atmosphere and continental water systems more than 100 times during a single million-year period. This oceanic circulation operates according to thermohaline dynamics that transport heat, dissolved chemicals, and biological nutrients between different ocean basins according to density gradients that respond to global climate variations on timescales ranging from decades to millions of years. Magnetic field reversals occur at irregular intervals averaging approximately 450,000 years, during which Earth's magnetic poles exchange positions through a complex reorganization of convection patterns in the liquid iron outer core. The reversal process typically requires between 1,000 and 10,000 years to complete, creating extended periods during which Earth's magnetic field strength decreases to levels that provide minimal protection against cosmic radiation and solar wind particles. These geomagnetic reversals leave permanent records in volcanic rocks and deep-sea sediments that provide paleomagnetic archives spanning hundreds of millions of years. The carbon cycle operates according to reservoir exchange rates that span 9 orders of magnitude, from the rapid exchange between atmosphere and biosphere that occurs on annual timescales to the geological carbon cycle that operates through weathering and volcanic processes across millions of years. Atmospheric carbon dioxide concentrations respond to human fossil fuel emissions on timescales of decades to centuries. Yet return to pre-industrial levels through natural processes requires hundreds of thousands of years of enhanced weathering and oceanic carbonate deposition. Glacial interglacial cycles driven by orbital variations in Earth's eccentricity, axial tilt, and precession create climate oscillations with periods ranging from 20,000 to 400,000 years, modulating global ice coverage and sea level through mechanisms that operate independently of atmospheric greenhouse gas concentrations. These Milankovitch cycles have controlled global climate patterns for millions of years, creating predictable variations in solar radiation that trigger ice sheet growth and decay according to astronomical calculations that can be projected millions of years into the future or past. Soil formation rates vary dramatically with climate and parent material composition, ranging from centimeters per 1,000 years in arid environments to meters per 1,000 years in tropical regions with high precipitation and temperature. The development of mature soil profiles requires tens of thousands to millions of years, creating terrestrial substrates that support complex biological communities through the gradual accumulation of organic matter and the chemical weathering of mineral nutrients from bedrock. The destruction of these soil systems through erosion or human activity can eliminate millions of years of pedogenic development within decades or centuries. Evolutionary rates measured through molecular clock analysis indicate that most species persist for periods ranging from 1 to 10 million years before extinction or speciation events create new taxonomic units. While higher taxonomic categories such as genera and families typically persist for tens to hundreds of millions of years, The longevity of evolutionary lineages correlates inversely with taxonomic specificity, suggesting that biological conservation operates more effectively at higher organizational levels, where environmental adaptation proceeds through species turnover rather than individual species persistence. Seafloor spreading rates at mid-ocean ridges average between 2 and 20 centimeters per year, creating new oceanic crust that moves away from spreading centers according to plate tectonic velocities that remain remarkably constant across millions of years. The oldest oceanic crust currently preserved on Earth dates to approximately 200 million years ago, indicating that the entire ocean floor recycles through the mantle approximately once every 200 million years through subduction processes that return oceanic plates to the deep interior. Stellar evolution timescales relevant to Earth's biological history indicate that the Sun has increased its luminosity by approximately 30% since the formation of the Solar System 6 billion years ago, requiring compensating decreases in atmospheric greenhouse gas concentrations to maintain surface temperatures suitable for liquid water. This faint young sun paradox illustrates how astronomical processes operating on billion-year timescales influence planetary climate evolution through mechanisms that dwarf all terrestrial climate-forcing factors. Crater preservation timescales vary dramatically between different planetary surfaces, with lunar craters persisting for billions of years in the absence of atmospheric weathering, while terrestrial impact structures undergo erosional destruction within tens of millions of years under normal Earth surface conditions. The terrestrial crater record preserves evidence of only approximately 190 confirmed impact structures from the past 5 billion years, representing a small fraction of the impacts that have actually occurred throughout Earth's history. Mountain building processes associated with continental collision operate over timescales of tens to hundreds of millions of years, creating orogenic belts that record the geological history of plate tectonic interactions through structural deformation, metamorphic mineral assemblages, and igneous intrusion patterns. The Himalayan orogeny began approximately 50 million years ago with the collision between the Indian and Eurasian plates, and continues today with ongoing crustal thickening and surface uplift that maintains active mountain building despite continuous erosional destruction. The mathematical precision with which these geological processes operate across deep time demonstrates the fundamental orderliness that governs planetary evolution, despite the apparent randomness of individual events such as volcanic eruptions, earthquakes, and mass extinctions. The statistical regularity of geological phenomena emerges from the operation of physical laws across temporal and spatial scales that integrate countless individual events into predictable patterns that persist across the vast duration of Earth's geological history. The temporal coordinates that define our current position within Earth's vast chronological expanse place human civilization at a moment so recent that all of recorded history occupies less than 1/10,000th of 1% of the planet's total evolutionary timeline, a statistical insignificance comparable to the final second of a year-long countdown. The Holocene epoch, which encompasses the entire span of human agriculture, writing, and technological development, represents merely the most recent 11,700 years of Earth's 454 billion year journey through deep time, a geological instant that barely registers against the immense temporal backdrop of planetary evolution. The rate of contemporary environmental change occurring during this brief human interval exceeds natural geological rates by factors measured in thousands to millions, creating conditions of planetary transformation that approach the magnitude of mass extinction events while operating across timescales compressed by orders of magnitude compared to previous episodes of global environmental reorganization. Atmospheric carbon dioxide concentrations increase at rates hundreds of times faster than natural variations preserved in the geological record, While species extinction rates exceed background extinction rates by factors that may approach those characterizing previous mass extinction events, the chemical signature of human industrial activity begins to appear in global sedimentary records around 1950, creating a geochemical boundary layer that will persist in Earth's stratigraphic record for millions of years as evidence of the brief period when a single biological species achieved sufficient technological capability to alter planetary atmospheric and oceanic chemistry on geological scales. This anthropogenic signal includes elevated concentrations of synthetic radionuclides, heavy metals, plastic polymers, and fossil fuel combustion products that have no natural equivalents in Earth's pre-human geological record. The current configuration of continental positions represents one frame in the ongoing continental drift movie that has played continuously throughout Earth's history, with the modern arrangement of land masses serving as a temporary snapshot of plate tectonic processes that will continue reshaping global geography for hundreds of millions of years into the future. Australia continues its northward journey toward collision with Southeast Asia. While the Atlantic Ocean expands and the Pacific Ocean contracts according to spreading and subduction rates that will eventually eliminate the Pacific Basin and create new mountain ranges along the margins of converging continents. Biological diversity during the current epoch reflects the recovery from the Cretaceous-Paleogene mass extinction 66 million years ago, with modern ecosystems representing approximately 65 million years of post-extinction evolutionary radiation that has produced the complex biological communities characterizing contemporary Earth. The current fauna includes evolutionary experiments such as mammals, birds, and flowering plants that might never have achieved ecological dominance if the dinosaur extinction had not eliminated the incumbent reptilian megafauna that controlled terrestrial ecosystems throughout the Mesozoic era. Global ice coverage during the present interglacial period maintains approximately 10% of Earth's land surface under permanent ice sheets. A relatively modest ice budget compared to the extensive glaciation that characterized much of the Pleistocene epoch and the complete ice coverage that occurred during snowball Earth episodes in the Proterozoic eon. The current interglacial conditions represent a brief, warm interval within an ongoing ice age that began approximately 6 million years ago and will likely continue for millions of years until continental drift relocates land masses away from polar positions. Ocean chemistry during the Holocene operates within the oxidized conditions established by billions of years of photosynthetic oxygen production, creating marine environments that bear little resemblance to the iron-rich, hydrogen sulfide-dominated seas that characterized most of Earth's oceanic history. Modern seawater chemistry reflects the equilibrium between biological productivity, continental weathering, and hydrothermal circulation that has maintained relatively stable ionic concentrations for hundreds of millions of years, despite ongoing inputs and outputs from geological and biological processes. The solar luminosity currently incident on Earth exceeds the energy output of the early Sun by approximately 30%, requiring ongoing regulation of atmospheric greenhouse gas concentrations to maintain surface temperatures suitable for liquid water and biological activity. This stellar brightening continues according to the nuclear physics of hydrogen fusion in stellar cores, ensuring that Earth's climate will require progressively lower atmospheric carbon dioxide concentrations to avoid runaway greenhouse heating that would eliminate surface oceans within 1 billion years. Technological civilization develops during a geological period characterized by unusually stable climate conditions, abundant fossil fuel resources, and moderate rates of natural environmental change that provide favorable conditions for the development of complex societies dependent on predictable resource availability and environmental conditions. The temporal coincidence between peak fossil fuel availability and human technological development reflects the specific geological timing required for both the formation of extensive hydrocarbon deposits and their subsequent discovery by intelligent species. The current mass extinction event proceeds according to mechanisms that differ qualitatively from previous extinction episodes, operating through habitat destruction, species introduction, and pollution rather than the volcanic eruptions. Asteroid impacts, or climate changes that characterized earlier mass extinctions. The biological selectivity patterns emerging from contemporary extinction show preferences for large-bodied, specialized, and slow-reproducing species similar to previous extinction events, suggesting that universal biological principles govern extinction vulnerability across different causal mechanisms. Genetic diversity within modern species reflects the demographic bottlenecks and range expansions that occurred during Pleistocene glacial cycles, with many species showing reduced genetic variation compared to pre-glacial populations due to repeated population contractions during Ice Age maxima. This genetic legacy influences the adaptive potential of contemporary species facing rapid environmental change, as reduced genetic diversity limits evolutionary responses to novel environmental challenges. The geological processes that continue operating during the human epoch maintain the same fundamental patterns that have characterized Earth's evolution throughout deep time, with plate tectonics, erosion, volcanism, and biological evolution proceeding according to physical laws that remain unaffected by human activities despite their influence on environmental conditions. Mountain ranges continue rising and eroding. Ocean basins continue opening and closing, and biological lineages continue evolving and going extinct according to processes that operated before human existence and will continue operating after human civilization ends. The perspective provided by deep time reveals contemporary environmental challenges as brief perturbations within Earth's ongoing evolution rather than permanent alterations to planetary systems. Though the magnitude and rapidity of current changes create novel conditions that have few precedents in the geological record. The resilience demonstrated by Earth's biosphere throughout previous episodes of environmental crisis suggests that planetary recovery from contemporary changes will eventually occur, though the specific biological communities and environmental conditions that emerge from this recovery remain unpredictable. The statistical probability of intelligent life developing on Earth during the brief window of favorable environmental conditions that characterize the current geological epoch appears remarkably small when viewed against the 4 billion-year history of biological evolution, suggesting that consciousness represents one possible outcome among countless alternative evolutionary trajectories that might have developed under different environmental conditions or timing. The emergence of scientific understanding during this geological moment creates the first opportunity in Earth's history for life to comprehend the deep time processes that shape the planet's evolution and will continue determining its future trajectory long after current species become extinct and new forms of life inherit the ancient Earth. In the vast stillness of deep time, where billions of years compress into moments and moments stretch across geological ages, Earth continues its ancient dance around the sun with the same steady persistence that has carried it through every transformation, chronicled in stone and preserved in the molecular memory of living things. The planet turns beneath starlight that has traveled across cosmic distances to illuminate landscapes shaped by forces older than consciousness, older than complex life, older than the very concept of observation itself. The mountains that rise from today's horizons will surrender to erosion's patient work, grain by grain returning to the seas that gave birth to the first stirrings of life in chemical darkness billions of years past. New mountains will rise from the slow collision of continents that drift across the planetary surface with the unhurried certainty of geological time, creating fresh stone from the compressed memories of ancient seafloors and the fossilized dreams of organisms that lived and died in oceans that no longer exist. The oxygen we breathe carries within each molecule the legacy of countless photosynthetic bacteria that transformed a poisonous atmosphere into the chemical foundation for consciousness itself, their invisible labor extending across hundreds of millions of years to create the conditions that allow thoughts to contemplate their own origins. Each breath connects us to the deep past through molecular threads that link the present moment to the first experiments with life's relationship to light and carbon and the patient chemistry of cellular existence. In the geological silence that surrounds all temporal moments, rocks remember the heat of planetary formation, the cold of global ice ages, the pressure of mountain building, and the gentle rain that has fallen steadily for billions of years, washing continents grain by grain into sedimentary layers that accumulate like pages in an endless book written in the language of mineral and time. These stone archives preserve the evidence of every major transformation, every mass extinction, every recovery, every innovation that has marked Earth's journey from molten beginning toward whatever future awaits in the cosmic darkness ahead. The stars that shine tonight include light that began its journey when Earth was young and molten, when the moon hung closer to the horizon, when no life had yet discovered the possibility of consciousness, contemplating the vastness of time and space. Other starlight now reaching Earth departed distant suns when dinosaurs walked beneath ancient skies, carrying across the cosmic void the electromagnetic signature of stellar fusion that connects our present moment to the deep history of the universe itself. Sleep comes to the Earth each night as it has for billions of years. Darkness spreading across landscapes that have witnessed every possible transformation, every experiment with life, every quiet extinction, and every patient recovery. In this darkness, geological processes continue their work with the same steady rhythm that has shaped continents and oceans since the planet first cooled enough to support solid ground and liquid water. The Earth sleeps and dreams in stone and time, and continues its ancient conversation with gravity and starlight and the mathematical certainties that govern planetary motion through space. Rest now in the knowledge that you are made of elements forged in stellar cores, shaped by evolutionary processes that span billions of years, sustained by atmospheric chemistry, perfected through countless generations of invisible organisms, and connected through the simple fact of existence to every moment in Earth's vast chronological expanse. The deep time that created the conditions for consciousness continues its work in the present moment, as patient and unhurried as it has ever been, carrying the Earth and everything upon it forward into the future with the same steady persistence that has characterized its journey through all the eons that came before. The wind that moves across the landscape tonight carries molecules that have circulated through Earth's atmosphere for billions of years, connecting every breath to the ancient processes that created the chemical conditions for life itself. Close your eyes and rest in the vastness of time, where the present moment takes its place in the infinite sequence of moments that extends backward to Earth's fiery beginning and forward into whatever transformations await in the cosmic future that unfolds according to the same physical laws that have governed planetary evolution throughout deep time.